Hello. So for this week's lab, let's look at those periodic trends. When we look at the energy required to remove an electron from an atom, what we sometimes call the ionization energy, we see two very distinctive trends in the periodic table. As we look at the groups, up and down, from top to bottom, the ionization energy decreases as we move down the group, which is telling us it's getting easier to remove electrons from the atom. Second, as we look at the trend within the period, the row from left to right, that ionization energy again decreases as we move from right to left. It gets easier to remove electrons from atoms which are further to the left of the period. And the reasons for this are both tied to the size of the atom. As we move across the table and down the group, the size of the atom is increasing as we move down the group. Remember, that's tied to a drop in the ionization energy. It's getting easier. And that's because the last electron is the electron furthest from the nucleus and the electron which has the weakest attraction to the protons in the nucleus. So it's the easiest to remove as we go down the group, as we add more shells, because it's further away from the nucleus. Now for that trend from right to left across a period, making it easier to remove electrons, it's because of the decreasing number of protons. We have the same number of shells as we look across a period. So it's not about the number of shells, because that isn't changing. It's about a diminishing number of protons as we move to the left, because that last electron is feeling less attraction to the nucleus if there are fewer protons. So to sum up, increasing atom size means increasing activity, because it's easier to remove electrons from bigger atoms. In the group, the atoms get bigger as we move down the group because there's an increasing number of shells. And across a period, it's easier to remove electrons as we move to the left because there are less protons holding on to those electrons. And so that atom size increase means that the atom and the element is going to be much more reactive. And if it's more reactive, it should produce more precipitate during a chemical reaction. Now, when you have the test tubes in front of you, sometimes it helps to let the reaction settle so you can see how much precipitate is produced. You're going to use a scale of negative up to 3 plus, negative for no reaction or no precipitate, 1 plus for a small amount of precipitate produced, 2 plus for a moderate amount, and 3 plus for lots of precipitate. You might have to run all the experiments in the group or the series to get an idea of what is or isn't a lot of precipitate. Remember, as you're working in the lab, use separate pipettes for each chemical reagent. It might be an idea to just communally use one pipette for each solution. You put the pipettes in the sharp spin once you're finished with them, but do not put the pipette bulb in the sharp spin. They can be cleaned and reused with other pipettes. And don't put the pipettes back in the pipette box either. Nobody wants to use your dirty pipette. And for our waste today, all of our waste goes into the inorganic methylene waste bottle. Now, one of the reactions you're going to do has to be done under the supervision of your instructor. That's the reaction of sodium in water. And let's take a look and see why. Now the sodium is reacting with water, and the sodium is giving electrons to the water as we form sodium hydroxide and hydrogen. That sodium burns with a lot of energy given off, and so sometimes the hydrogen which is being produced ignites, as you see in that last video. Although this tends to be one of the more excitable examples of the sodium reacting with water, but it's by no means the worst. Once in a while, we sometimes get a very violent reaction. So it's important that you're supervised for this experiment, and important that you use the fume hood and use the chemicals you're supposed to be using.
Itself is giving off a lot of heat. As it dissolves, just in case. Giving a lot of heat.
Now the explosion we have here is not the hydrogen that's being produced. It's probably the stripping of electrons from the sodium metal, creating this large cluster of positively charged ions. And positively charged ions repel each other, and this is much more likely to be the explosion. It probably doesn't involve the hydrogen. However, reactions like this normally only happen when we're not using the correct chemicals. These students were later found to have reacted the sodium with hydrochloric acid, and you're not supposed to use the hydrochloric acid for sodium, just use water. Take due care and diligence, and there won't be any accidents.